This is 5.5, part 2. All right, last time we were on example 3, and we were about to do part D of that. So y equals log base 3 of the square root of x divided by x plus 5. Well, my base reaction to this one is to simplify the right-hand side using properties of logarithms. So I'll do this one thing at a time so as not to confuse anyone. The first thing I would do is I don't like radicals when I'm trying to find derivatives. So I'm going to rewrite the square root of x as x to the 1/2. Then the logarithm of a quotient is the logarithm, keep the base 3, of the numerator minus the logarithm base 3 of the denominator. Notice that's in parentheses because it's more than one term. Then, to continue simplifying, I'm going to bring that 1/2 out in front of the logarithm, because the logarithm of a power is the exponent times log base a, whatever a is, of the base of that power. And the second thing, and that's as simple as that goes. So then I would use implicit differentiation. Oops. And take the derivative of both sides of that. The derivative of the left side is dy dx. The derivative of the first thing is the constant 1/2. And that's almost like ln of x, so I'm going to get 1 over the something I'm taking the logarithm of, but that then has to be multiplied in the denominator by the ln of the base of that logarithm times the derivative of x, which is just 1. And then the derivative of log base 3 of x plus 5 is same idea. 1 over the something, and in the denominator, multiplied by the ln of that base, times the derivative of x plus 5, which is 1, which of course I really didn't need to write that. That's okay, it's not going to hurt anything to have written it. So if I want to simplify this, simplifying here would mean do the subtraction. So I'm going to write this as 2 ln of 3 times x. Leave some space, you'll see why in a second. I'm going to write this as, well, I'm not really changing it, I'm just taking away the times 1. But I have some clear space to the right, and you'll see why I need that. So to add fractions, we need a common denominator. So the denominator on the left has 2 natural log 3 and x in it. It does not have the x plus 5, so I need to introduce the x plus 5 into that denominator by multiplying that fraction by x plus 5 over x plus 5. The second fraction doesn't have the 2, so I'm going to introduce the 2. It doesn't have the x, so I'm going to have to introduce the x. And it does have the ln of 3 and the x plus 5 already. So that's all I need, so I have to multiply by this form of 1 for the second fraction to get a common denominator. Of course, that was my goal. And so I'm going to have x plus 5 over our common denominator minus 2 2x over our common denominator. Do you see why we abandon using x as multiplication? Because otherwise that denominator would look like I'm multiplying a number by x plus 5. So we don't use x for multiplication. I guess the only thing that we hold on to that in is in scientific notation. We do use the x for that. It's also used for vector multiplication in something called the cross product. So anyway, those are the only vestiges of using x for multiplication that we still use. All right, so the rule is once we have common denominators, we subtract the numerators. So x minus 2x is negative x, and 5 minus 0 is positive 5. So I can write that in front of that minus x if I want to, all over our common denominator. And that's my final answer. And of course, we would like for that to be a single fraction and in factored form, because if we were about to find critical numbers by setting that equal to 0 or finding out where it fails to exist, that would be a good form for that purpose. Okay, so that was example D. Now let's talk about integrals. Sometimes we're going to be integrating an exponential function that is a base that's not e. When you do that, there are two options. Which I love when you have options, and I actually end up saying, yeah, they all stink except for the one I'm going to do. We can convert everything to base e using the formula a to the x equals e to the ln of a times x, and then integrating. Or you can just integrate directly using the integration formula. That's going to be my preference. I'm not even going to show you the long way on that other technique. If you want to do it and you can do it correctly, hooray, do it. Okay. So here, the rule is for the antiderivative of a to the x, it's almost the coolest function ever. So we're going to get back a to the x. Now, when we did the derivative, we multiplied that by the ln of the base, so times ln of a. But because we're doing the antiderivative, instead of multiplying by ln of a, we'll divide by ln of a. So it'll look like fraction 1 over ln of a, which is a constant, times a to the x. And then, of course, don't forget your constant of integration. Okay. So that's going to be my suggestion, is that that's the way we do it. So that's a formula, like all the other ones I've introduced, that you should probably make sure you commit to memory. Oh, and by the way, a to the u du, when you integrate that, that's also going to be 1 over ln of a to the u plus c. Okay. Anyway, so because this is not base e, the antiderivative of 2 to the x, which is almost the coolest function ever, we'll get back that 2 to the x, but then we have to remember to multiply that by 1 over the ln of the base of that power, so 1 over ln of 2, times 2 to the x plus c. Okay. So we know, and this is review, that if we have the derivative of a power of x, where x is any real, where n is any real number, that's the power of x, the rule is you bring that power down in front and multiply it by x to the reduced by 1 power. And if that happens to be instead of a plain x, it's some function that's raised to the nth. Its derivative follows the same rule, n times our something to the n minus 1, but then the chain rule kicks in, and we have to multiply by the derivative of the inside function, represented by du dx. So, let me ask you a couple of maybe tricky questions. What's the derivative of e to the e? Well, we'll see if I tricked you or not. E is a number, and any number raised to a number is just a number. And so this is asking you for the derivative of a constant, and the derivative of a constant is 0. I hope you didn't bring down e and multiply it by e to the e minus 1. Oops, if you did. E is not a variable, so you can't treat it that way. Okay, now what's the derivative of e to the x? Hint, coolest function ever. Well, of course, that's e to the x. Hooray, you got that one right. Okay, now what is the derivative of x to the e? Well, since e is a number, that's x to a number. It's not x squared or x cubed, but we follow the exact same rule. So we bring down that constant e in front and reduce the power of the numerator by 1. Now, I can't simplify e minus 1 any more than that. So be careful. E is a number. It's not a variable, and you've got to treat it like a number that you're just maybe a little bit less used to seeing than others. Okay, now the next question is, what is the derivative of x to the x? Well, x is a variable, and it's a variable in both positions. Both the base and the exponent are variable, and that is not covered by any of the rules that we already know. So what we're going to have to do to find this one is, let's say that y is x to the x. And anytime you don't want x in the exponent and it's there to begin with, you're going to want to use logarithmic differentiation. So take the natural logarithm of both sides of the equation. All right, so the reason we do that on the right-hand side is to get that variable x out of the exponent. So we're going to use the property of logarithms that we know is true and bring that exponent down in front as a multiplier by the ln of the base. Then we're going to use implicit differentiation. That is, we're going to take the natural logarithm on both sides with respect to x. Okay. And so the natural logarithm of something is 1 over, oops, a little bobble there. Let me get rid of that. Yeah. The derivative of natural log of something is 1 over that something times the derivative of that something. And the derivative of an expression in x is, hold on, I see something else I want to get rid of here. I don't know if you see it on your screen, but I see it on mine, so I'm going to get rid of that. Sorry. I just don't want you to think something all of a sudden popped up there that doesn't really belong. Anyway, since x ln of x is a function of x, we follow the regular derivative rules because we're differentiating with respect to that same variable x. And that's a product, so I'm going to use the product rule. First function times the derivative of the second one plus the second one times the derivative of the first one. So I'm going to take one step here to simplify the right-hand side. X times 1 over x is 1, and ln of x times 1 is just plain old ln of x. Then, to solve for dy dx so that we know what the derivative of that original function is, we multiply both sides by y. Notice the insertion of parentheses to protect the fact that that right-hand side has more than one term. Then, to finish the problem so that our answer is completely in terms of x, I'm going to replace y with the original value of y that we started with, x to the x, times 1 plus ln of x. And so that answers the question of what is the derivative of x to the x. That question mark up there, there's the answer right down there at the bottom. All right, now an application. An amount of $P is deposited in an account at an annual interest rate R, which is going to be written in decimal form. So if they say 7%, that's 0.07, to make sure you do that. What is the balance in the account at the end of 1 year? Well, the answer depends on the number of times n that the interest is compounded during that year. And the formula that we use for calculating that interest is the amount of money you'll have after a year is P, which is the principal amount, the original amount you had at the beginning of the year, that's the amount invested or deposited, times 1 plus R, which is the interest rate in decimal form, divided by n, the number of times it's compounded during the year, raised to the nth. So let's talk about different values of n. So if you have like a, trying to think of the type of account that you would know. Well, an old CD, I don't know if you know what that is, certificate of deposit. It would get interest once a year. And so the number of compoundings, if it's like a certificate of deposit, if it's one time each year, then your n is 1. Simple interest. And if it's compounded for some reason semi-annually, so twice a year, called semi-annually, that means n would be 2. If it's quarterly, how many times does that happen each year? 4 quarters, so n would be 4. If it's compounded monthly, and this is like a lot of bank accounts and credit cards and things like that are done monthly, n would be 12. If it were done daily, it would be n equals 365, except for leap years, when it would be 366, etc., etc. So that's the number of compoundings per year, depending on how often they recalculate how much you have based on the interest rate. Okay, so that's that formula. So if I had, for example, $1,000 that I put into an account, and I was interested in knowing what would happen if this is at an 8% interest, which is actually really good, I would do that. If it's compounded n times a year, let's just make a table of values. And if you substitute all of those numbers in, except for n, the amount of money will be $1,000 times 1 plus 0.08. Remember, 8% will be written as a decimal over n to the nth for this problem. And so if you pick up your calculator and put that in with n equal to 1, so once a year, semi-annually, so twice a year, quarterly, 4 times a year, monthly, so n is 12, and yearly, Let's assume it's not a leap year. And by the way, for all these calculations, if they say yearly, since 3 out of 4 years are not a leap year, that's our assumption, unless it's a multiple of 100, and then it is a leap year. Did you realize that in 2000 it actually was not a leap year? Interesting fact. Anyway, that's a side fact that we just don't care about. So if you do that, and let's round to the nearest cent, so to 2 decimal places. If you compound once a year, it's $1,080. If it's twice a year, that's $1,081.60. And quarterly, that's $1,082.43. So the more often they compound, the better the return is. Monthly, like my checking account, I get monthly interest, $1,083. And daily, $1,083.28. So it is increasing, but the amount it's increasing by seems to be slowing down. Like from 1 to 2, it went up by $1.60. But from 12 to 365, where n was increasing a whole lot, it only went up 28 cents. So as n gets bigger and bigger, the difference in what you're getting is decreasing. And so, in other words, there's probably a limit to this. And so if we took the limit of this expression as n approached infinity, if you could compound like all the time, and that actually has a name, it's called continuously compounded interest, you would want to know what this approaches as n approaches infinity. So you could go back to your calculator and put in bigger numbers for n, like 1,000, 10,000, etc. Just make it bigger and bigger and see what it's approaching. And that would be like if you had continuously compounded interest. To answer this question, and I'll come back to it in just a second, we need to know this limit right here. The limit as x approaches infinity of 1 plus 1 over x to the x, so that looks sort of like our formula up there, is the same thing as the limit as x approaches infinity of, get a common denominator and add, that'll be x plus 1 over the common denominator x, all raised to the x. That's e. And so if we use that, you can, and again, you can test this idea if you want to in your calculator. Type either one of those expressions, 1 plus 1 over x to the x, or x plus 1 over x to the x, and just make x bigger and bigger and bigger. You'll notice that your answers for that power get closer and closer to 2.71828 when you get up to around 1 million. That's what you're going to see. And that is the approximate value of e. So if you went all the way to infinity, it would actually be e. 2.718. 2.71828. Yeah. So that's an approximation of e, and in fact it is e when x goes to infinity. So as it turns out, we can take the formula that we had for interest and make the number of compoundings go to infinity. And this is going back to the general thing. I'll go back to our specific one with the $1,000 investment and all that in just a minute. We have to do some aside work here. So we take this formula for a, take the limit as n approaches infinity. So what I want to do is I want to have you realize something here. If I said, what is 1 over the fraction n over r, I would hope you'd say, well, that means the reciprocal of n over r, which is r over n. I hope you get that. You might come across that idea by thinking, well, to divide fractions, you multiply by the reciprocal of the denominator. But at any rate, you should know that that's what r over n is. So if that's true, then I'm going to, in this expression, replace r over n with 1 over n over r. And if I make that substitution, this will still be raised to the nth power. Okay. Now, if I were to, and this is all going to seem like, well, why are you doing this? It will hopefully become clear. But if I ask you to multiply n over r times r, what would you get? If you thought of that as r over 1, when you multiply, wouldn't you get nr over r, which would simplify to be n? Right. So I'm also going to rewrite that exponent in a different form as n approaches infinity. And what I can do is I can take that power of the binomial and rewrite it as n over r raised to the r, right? So it was n, and I'm saying it's the product of n over r times r. And remember, the power of a power means you're multiplying the exponent. So I'm rewriting that as n over r as the power of the binomial to the r, which would simplify back to what we had just a second ago. Again, I'm sure you're thinking, who thought that was a good idea? Anyway, it actually works out nicely. Now, I'm going to let x replace n over r. Okay? Then, as n goes to infinity, and r is a constant, that would mean that n over r would still approach infinity, which implies that x would have to approach infinity as well. So if I do a substitution and rewrite this in terms of x, when n goes to infinity, x will go to infinity, as we showed over to the right, p, and this is going to be 1 plus 1 over x to the x raised to the r. Okay, now before I get much further, I want to use a couple of properties of limits to simplify this, hopefully a little bit. P is just a number that is your value of your investment, so it's a constant. And remember, the limit of a constant times a function, you can pull that constant P out in front. And I could have done that earlier. I just decided to wait and do it now. And I don't want to do too much at once. I don't want to confuse you. So I'm making that just that one change. And then we have a property of limits that says if you have a composition whose limit you're trying to find, you can take that limit inside and work from the inside out. So take the limit of the inside thing inside of the outer function. So that's what I want to do next, is I have something raised to the r. Something to the r is my outer function. So I'm going to take that limit inside. To take the limit of the power 1 over 1 plus x to the x. And then there's the outside function to the r. And that inside thing, if you may recall, please, is that that's one of the definitions of E. So that whole inside thing becomes E, which is raised to the r. So, going back to our problem with the $1,000 investment and an interest rate of 0.08, what would the limit be? That's what we were trying to find earlier. I'll highlight it in a different color. Well, what would that limit be? And I had to do a whole lot of side work to kind of figure that out. But as it turns out, according to the work down below, that's going to be P, which is, in this problem, 1,000, times E to the R in decimal form, so that's 0.08. And that is how much money? 1,000 times E to the 0.08 is about $1,083.29. So going from a year, once every day, once every day, 365 times in a year, to continuously compounded interest, looks like we gained a whole penny. Big whooping deal. But anyway, that's just theoretically, if you could just continuously compound it, that's what the answer would be. So that's kind of a proof of why that works. Okay. So now it's not necessarily true that you're going to leave this as an investment for only 1 year. So what happens if it is for longer than 1 year? The formulas change slightly. There's something that we kind of implied was 1 for 1 year that we're going to put in as t for the number of years you leave it in there. So this is going to look very familiar so far. Looks just like what we had before. But the exponent is n times t. And of course, if it's 1 year, t would be 1, and that would just be n, which is the formula we used before. And if it's continuously compounded interest for longer than 1 year, then it becomes the principal times e to the r t. Where, of course, if t is 1, you get the formula that's up 2 lines from there, p times e to the r. But this is if you have it for, like, say, 5 years, t would be 5. The way I remembered this one, when I first learned it, Pert shampoo was a really new, cool shampoo. And so I always just remembered Pert, P-E-R-T. And, of course, the r and the t are exponents. But that's how I remember this formula. I don't know if that'll help you. I don't know if Pert makes a big difference to you. Anyway, as a shampoo. Let's go to example 6. A deposit of $2,500. So that's our principal amount, $2,500, is made in an account that pays an annual interest rate of 5%. So R will be 0.05. Find the balance in the account at the end of 5 years. So T is 5. If the interest is compounded quarterly, monthly, continuously. Okay, so monthly. For monthly, that means N is 12. And that means we're using the first of those formulas. The second one, the PERT one, is only for continuously compounded interest. So this will be 2,500 times 1 plus 0.05 divided by 12, that's what n is, to the 12, which is what n is, times t, which is 5. Okay? And you simplify that, and you should get, you put this in your calculator. This is obviously a calculator active kind of question. $3,205.09. Remember, we're rounding to the hundredth because we're rounding to the nearest cent when we're doing money problems. Okay, B. Monthly. Oh, my goodness. I said quarterly and then went straight to n equals 12, and that means I messed up. So, actually, that was part B, monthly. And this is going to be part A, quarterly. Sorry about that. I looked at the second one and just kind of got mixed up. Oh, and that's the wrong answer, because I was looking at the answer for the, yeah, I messed up. So I'll own it. Let me erase this. Hopefully you didn't get too mad at me. You didn't put that in your calculator and say, hey, wait, that's not what I got. Yeah, I messed up. So let me fix it. So if we're truly doing the monthly, which is part B, the answer you should get is $3,208.40. I'm so sorry I did these out of order. That's irritating, I know. Okay, so let's go back and do quarterly, which would be n equals 4. Okay, so that's 2,500 times 1 plus interest rate 0.05 divided by n, which is 4, raised to the power of 4n times t, which is 5 for 5 years. And that is the answer I gave you earlier, the $3,205.09. That was the correct answer for A. I just actually wrote the work for B. So I now have that fixed. Make sure you take note of which one is which. The pink letters are correct. My goodness. Anyway, C is continuously. So that means we're using the other formula. So that's going to be A equals PERT. So the principal is 2,500 times e to the r, which is 0.05, times t, which is 5. Type that in your calculator, and you should get $3,210.06. Okay. Okay, that is the end of section 5.5. I will see you in class.